that was taken of Vera shortly before she went back to live with her family. This is from Sethanne Howard at the Washington Academy of Sciences, and I think 2012. So anyway, I had the pleasure of seeing her only a few times. She came with her husband and with Ralph Alpher and Robert Herman out to visit Goddard Space Flight Center when we were preparing the Cosmic Background Explorer for launch. And even and Bob and Ralph even came to the launch itself. So that was a lovely reminder of things that happened a while back. I think one of my themes today is springs from actually what Jim was telling us. We made our discoveries because people had new technologies. He told us about new photographic film that was better than before, photographic plates, and then image intensifier tubes that enabled Vera to do the work that she did with Kent Ford. So I like to think about that great trend and think about where we came from and how far we could go. So remembering back to when I was young, in 1957, the Soviet Union put up a satellite and scared the crap out of us. Even though it was not a surprise and we had been totally warned ahead of time, people were not paying attention. There's my computer. The first one that I had was that one in the middle, the little round slide rule. And I couldn't afford the new HP 35 when it came out because I was a graduate student and I didn't have that money. On the lower left, you see what Building 2 construction looked like at Goddard in 1958 or so. It was different then. People may not remember. And there was the great supercomputer, the IBM 360s, which could certainly be exceeded by my cell phone now. So I'd like to think about how far we've come because I'd like to see thinking about how far we could go. So we have a chart from Goddard illustrating many missions that we did in the 1960s. Way back then, many of the satellites we built, you could actually reach across, and you could carry them if you had a few people to carry them with. Then they got bigger and bigger. We started putting up astronomy, the orbiting astronomical observatory, and from there we got even more ambitious. In 1976, I came to Goddard Space Flight Center, and 3 years later we launched the IUE into space. Telescope about that big, but you could sit in the control room at Goddard and drive it and take the data and decide what you wanted to do. It was like running an observatory on the ground. The same team that built that observatory was the first team to help us design the COBE satellite, which went up a few years later. So in those days, we designed things with sharp pencils on big pieces of paper. And it's hard to remember those days, but it was all different. When I see the simulations that people do in the computers, I'm feeling very jealous. And a few years later, we had another collection of observatories we were building. There's the Space Shuttle, the Hubble Space Telescope, which went up on the shuttle. We built the MMS, the Modular Multi-Mission Satellite. We thought we were going to make several of those, and we were going to reuse the parts. Well, that didn't much happen. We did go to service it, though, and we got one use out of the multi-mission concept. That also is coming along. Back in 1985 or so, NASA said we need to explain to Congress what are the great questions that are to be examined so that we could understand why we need 4 great observatories, from infrared to X-rays to gamma rays to Hubble. And so all of these questions were wide open at the time, and some of them really still are, but we've made a whole heck of a lot of progress. How did the universe begin? Well, that's what cosmology has been about lately. New laws of physics, well, David says maybe there's no new laws of gravity, but there sure are other interesting things. Dark matter, well, people had guessed that it might happen, I suppose, but no, there wasn't much evidence for it back in those days. We still are learning things about how stars die. I just heard this week that there's a sort of super-duper supernova that can make neutron-rich elements, and the neutron star pair merging isn't the only path. The one that's exciting young people a lot these days is how are the planets formed and how did life start? And almost every young astronomer that I meet wants to work on that. But that's pretty cool, so who knew? When I was a kid, we knew the answer. There wasn't anything out there, and Earth was very rare and life was impossible. So unless there were a divine intervention. So anyway, now we have a different opinion. So we had a couple of cryogenic missions. The Infrared Astronomical Society satellite went up, and then we decided to use almost the same cryostat to carry up the COBE satellite, to measure the Big Bang radiation. There's the spectrum and the anisotropy that we first measured. When we designed the COBE, by the way, we did not know what there was to look for. Computers had not yet caught up to tell us what we should be aiming for. So far, nobody's done better than that spectrum, but we do know now how to do it better if we want to. We could push beyond that accuracy, which ended up at 50 parts per million. We could probably go down to 50 parts per billion on that spectrum if you want it. You got to ask for it hard, because that's a really hard experiment, but we do know how to do it. We certainly have done a lot better than those spots already, as Chuck Bennett's WMAP mission already proved. And congratulations to Chuck and the team and David. I don't know how many of the rest of the team is here today, but at least some. So what else did we learn? Well, from COBE and WMAP, we figured, yeah, we can do cryogenic stuff. Then we flew the Hubble. My chart's already old because Hubble is actually over 29 years old. Can you imagine? It's older than a lot of people. It's older than some people that are using it. So you can see in there in the middle what happened when we got to fix it. Everybody knows it was out of focus, and that was a huge, huge disaster for us. But as you know, we figured out what to do. Astronauts have been up 5 times to the Hubble, and they're not planning to go again. The current plan is when it gets old, we're going to latch on a rocket engine of some sort and aim it for the Pacific Ocean or push it way out. So also that picture on the right, that was, as I remember, the day when we put them out. Well, it's a AAS meeting, and the internet crashed because everybody wanted to go see those new pictures. That's another marker of how rapidly things have changed. So Hubble showed us a lot of things we weren't expecting, and that's an example of the black hole in the middle. So we have learned a lot more about flying more satellites. They are common now, and they're getting to be so common that we worry about them because they're so common. So I showed you already, or mentioned, that we had this SMM to be a multi-mission modular spacecraft. We did actually visit it with the space shuttle and updated it. But now, by the way, over 2,000 CubeSats have been flown, and many a university can afford it. Many a university will apply to NSF to afford it better. Anyway, the remarkable things can be done with little satellites, and I am thrilled to see that. So how far can we go? Well, we have not yet run out of exponential growth. So for computers, it has slowed down a lot. My laptop here I got the same speed that it had when it was 8 years old. 8 years ago. So that hasn't happened very much anymore. Different things will have to happen for that growth to continue. But in the space business, we have had a 40% increase in the launch rate in 8 years, which is a 4% compound growth rate. That's not too bad. And companies are getting into that, so many, many more launchers are coming. There's an infrastructure that we all use that you can't see, but it's getting better and better. When I say I need to build a telescope, can I draw it? Yeah, no, we draw it in the computer. And when you want to see, will it all fit together? Well, the parts will fit together because you designed them all in one computer. When we built the COBE, you sent your drawings off to the machine shop, and they came back and they didn't fit. They had to go do it again. So things have changed a lot about how well we can do things. How rapidly our telescope mirror size is going up? Well, about a factor of 7 in area in 31 years between the Hubble and Webb telescope launches. That's not such a measly rate of increase. But it does tell you the next one of that category of jump is going to be a long time in the future. I don't know how long it takes, but that's why we have a decadal survey, to say what are we going to do next. Similarly, the ground-based telescopes have been also increasing very rapidly in size because we have new technology coming for us. So that's fantastic. So we have done, however, many things in spite of external trouble. This is a more NASA-specific chart, but a couple of things that happened. The tornado came by a few weeks after 9/11 and just about got us. Hit the University of Maryland. We had a little earthquake 10 years later, and it bothered us a bit, but nothing really bad happened at Goddard except we all had to run out of the building. Then we had the giant storm that ran through Goddard and ripped all the electricity out, and so we had a total loss of power, despite all of the things we do. Plus, we've had a few government shutdowns and 10 furloughs, and we're still all here. Thank you much. So how do we get to do all these things? Well, this is an interesting perspective. Neil deGrasse Tyson and Avis Lang put out a book that said, by the way, we astrophysicists have been benefiting and working with people with military interests for a long time. And it's a really startling documentation of that. If you have a sort of nonviolent or pacifistic approach to life, well, this is a reminder you can't escape society. On the other hand, if I want to order a telescope from an aerospace company, they say, I can build you one of those. I've built some before. And so I think this is a sort of arithmetic point that says, yeah, we can afford things, we can do things, we can launch big things, but it'll take us a while. But this is a reason to think that it is all possible, and we're not going to run out of things to do. I think everyone has seen the LIGO designs, and I'm thrilled to say that we're about to get daily announcements one of these days. I heard that you can get an app that tells you when something happens, and of course we need to go follow up everything. TESS is up there, and we're going to get many, many, many targets to look at for the Webb telescope looking at exoplanets. Who knows which ones will be the most exciting. Here's a picture of the ALMA, which I got to be a reviewer for before it was even called ALMA. I thought, this is the most complicated thing I've ever heard of. It is much more complicated than the Webb telescope, but it is on the ground. And so when it isn't happy, you can fix it. So the picture in the upper left was one of the most startling ones I've ever seen. Those are rings of dust orbiting around a new star, and it is claimed there are planets growing in those little rings in between. So isn't that an amazing thing to be thinking about, that our society, our human society, has figured out a way to look for that, as well as doing cosmology and a lot of other things. So I guess everybody knows I'm the senior project scientist for the James Webb Telescope, but I didn't want to say very much about it because John Gardner is also giving a talk about it today. There's the standard picture of it and a statement that we are planning to launch it in March of 2021. We have now got the telescope in California along with the warm part of the observatory, and they're supposed to be assembled together this summer, and we will then do the last vibration and cold test and deployments and send it off to the launch site. Just an illustration of one thing that people will do that we never thought we'd be able to do. We know Europa has ice over an ocean, and there are places where the water is coming out. So you can watch those at many different wavelengths, and we're going to, of course, point the telescope over there to see what happens. A long time ago, it was thought, well, we know it's got an ocean. You're going to have to drop a nuclear reactor on it to melt your way in. Now you don't think so because you can see the cracks and you can see where the samples are coming out. Let's just go get a sample. WFIRST is coming. I don't know what we're going to do exactly because some of these things are under discussion, but it will be a tremendous step forward in what we can do about dark matter, dark energy, and exoplanets. What's intriguing me even more now is the possibility of truly gigantic telescopes on the ground, which there are 3 of them under construction. They're coming. And I think what people might not appreciate is if you could get adaptive optics working on the biggest one, on the lower right-hand corner, you could angular resolution of 3 milliarc seconds. So it's about 16 times the aperture of Hubble. So wouldn't you like to have that? Well, nobody's talking much about how you would do that, but I think we should aim for that. And I'll show you a little thought of it later. Of course, this is how we do it in general. We've got adaptive optics. And the logic of it is the same, regardless of the wavelength and so forth, but you have to have something that tells you if you're properly focused. So you do it pretty well on a bright star. It's harder to do it if you don't have a star where you want to look, and if that's actually the big challenge. And you might not know and appreciate, but your eye doctor may have something very similar in his or her office because they want to see what's the back of your eyeball look like. and they have to look through the distorted lens that you have. So it's the same logic. Now, who would have thought that our mathematics would lead to thousands and thousands of optometrists and ophthalmologists and millions of patients having their adaptive optics examination. And by the way, if you're a football player and you need to see with 20/10 vision, you can get your fix based on this same mathematics. Then you can win your football game. So now my thought is, well, wouldn't you like to have your orbiting laser beacon to focus your telescope on? Well, you can't put a natural guide star wherever you want, but you could put a laser beacon wherever you want for at least a while. What do you have to do? You need to put it in a long elliptical orbit, at least 170,000 kilometers up, so that the velocity of the laser beacon can match the velocity of the observatory, and do it for a while. If you don't want to put any propulsion on it to move it while you're observing, then you can still have it hover in the right place for up to a couple of hours, 9,000 seconds, according to the paper I cite there at the bottom, Marlowe et al. So you could do this if you want. And what does it take? It takes a pretty small satellite because you only need to focus your laser beam on the observatory. If you wanted to illuminate the whole Earth with a laser beam, that's a lot of power. If you just want a 1 kilometer spot on the ground where only one observatory is going to notice that you're there, you can get well under a watt of power is good enough. Because what you have to simulate is a roughly 8th magnitude star. So nobody would know you were there unless you knew to look. But you can do this. So, by the way, if you want to study faint stars, 30th magnitude star in a minute of exposure could be done. So I think we would be thrilled to have this if we could do it. So more hardware coming. Well, Vera's going to have her telescope. I hope this is fully approved at some point that we can really name it with and for her. But this is another example of how the computers aren't quite good enough, and an illustration of what amazing inventive engineers and scientists can do. When they said they were going to make a degree field of view and a 3.2 gigapixel camera, I thought that must be impossible, but it's not. So I think there will be amazing things coming for us. LISA is coming. We are building it, or at least we're trying to build it with Europe. And so there will be another extension of gravitational wave astronomy. We are not short of ambition. Here is an idea for a 30-meter telescope in space. This was done quite a few years ago by Bill Oegerle with a study team at Goddard. And this is a story about how you would put a great many hexagons in place and hold them there with tensile structures and the like. I would say it's not impossible. It's pretty hard. We're not going to do it today, but maybe that in the far future, 30, 50 years, we may be able to do it. We'll need pretty good robots because we're not going to go up there with astronauts with screwdrivers to do that. Another idea I've been thinking about lately is this one. How about a star shade to look for exoplanets using telescopes on the ground? I showed you the telescopes. I talked about adaptive optics, talked about matching an orbit. What if you put a star shade way out there in that orbit too? We think you could do this. And that a solar system at 5 parsecs away, you could see Earth, Venus, and Mars in a minute, and you could get their spectra in an hour. And you would be interested to know whether oxygen and water could come through. I think they do. So you would be able to tell if that's really an Earth out there. On the other hand, if it's really dry or it doesn't have much air, you might not know it had any, because molecules blocked by our molecules, you would not see them so well. At any rate, it's not impossible. So we've been doing a study at Goddard and with Jet Propulsion Lab to figure that out. So send in a white paper soon about that. So can we really pay for all this? Well, maybe. There are other people that need big stuff. People that worked on this airborne laser came and worked on the Webb telescope also. For a while, the boss of NASA was Dan Golden, and he knew all about this technology. So when he heard we wanted to fly a segmented telescope, he said, yeah, we know how to do that. Well, we didn't really, but we can, and we are now. So I think this could happen. This is an extraordinary future that we could imagine. There is plenty of justification for building all the hardware that we could imagine. We are certainly not running out of questions, and other people are helping grow the infrastructure that it takes to make this all possible. So thanks, and let's cheer for the people that build stuff. Thank you.
Much for that very inspiring talk.
This is not going to happen.
Oh, it's not finished?
Yeah, that's my last trick.
Sorry. Okay. Questions? Questions from young people who are going to use all these great toys or build them. Yes, David.
Not young, but
Younger than me.
as we think towards the decadal survey and think about making these choices about what do we build next, what do you think are the most important lessons that we've learned from James Webb?
Well, always it's hard to get the right answer the first day when you think of something. When somebody says, I'm going to build you this and it's really wonderful and really cheap, you should never believe that. And if somebody says, John, you have to build it, and it's only going to take this much time, you should never believe that either. On the other hand, if the game is worth it, we should do it. The things that Webb's telescope can do, nobody else could ever do in any other way that we know of. And the things that other equipment is designed for, they also answer questions that could not be answered in any other way that we know of. So if you want to know the answer, you have to do something in this general direction. And so it's only a question of how much do we want to know, and can we get the resources to do it? So that's sort of my opinion. We should not give up on hard problems just because they're hard.
Well, that reminds me of, we're on the 50th anniversary of going to the moon, and the famous quote from Kennedy, we choose to do this because it's hard. But my real question was, yesterday, France told us to not be constrained in our thinking, to think really big and forget about budgets. And your comments here reminded me that every project starts out, it's going to be the best ever, and it's going to be easy to do, and it's going to cost $1.50. And there are bumps along the road, and you're not measured by that first thing, but you're measured by what you do when you hit the bumps along the road. But if you had to give advice, this is sort of following up on David's question, and of the kind that France gave us yesterday, what would your advice be to people who are thinking about the decadal survey from the space side? So France said, from the ground side, think big, don't be constrained by budgets.
Well, I think I would echo her advice, and I would say that Congress isn't actually that excited about little stuff. When you go visit their committee room and you see what they have on the wall, it's space pictures of the Hubble images, it's the space shuttle, and a few other things up there. They are proud of having sponsored what we do. And so I think we should continue to give them something to be proud of. That means ambition. It means actually delivering on the ambition, which is harder than it sounds, because you can't say, well, I'll just say it's a long jump between John Mather draws a sketch of a big telescope and a short person to we launched it. And so, and none of us really have the wit to imagine all of the steps that takes. So that's my recommendation is be ambitious, have a thorough scientific inspiration behind it, and basically let the decadal survey do their thing, because they will answer that question.
Of all the new astrophysical insights that JWST will teach us, which one do you think will have the most profound effect on shaping the human perspective?
I'm kind of hoping that we see something that nobody ever even thought to look for. And that would, of course, remind us that's why we build new equipment, because you can't see stuff that you don't know is there unless you look. I think I'm anticipating we will have some spectacular discoveries in the early universe, that there's some process making some unexpected form of early galaxy that all merged into something else, so we don't see a current trace of them. We could find big surprises about exoplanets. We could find that, although there are lots of them out there, that none of them are like Earth. So that won't all come directly from the Webb, because we can't see Earth-like planets around Sun-like stars very well, if at all. We could get some interesting surprises about how the stars are being born inside their dust clouds. So what's the cultural impact of this? I think we're going to have beautiful pictures that appear in every coffee table, in every textbook, and that'll be the cultural impact of things. For our scientific impact, I think we'll say, gee, I'm sure glad we did that. I'm hoping that's what we have.
Thinking again about the 50th anniversary of the moon landing, a moonwalk, I think we have a danger in terms of our excitement excitement quota, which is the competition between human exploration and scientific exploration for resources. And I wonder what your perspective in the long run on that is.
Well, good question. I heard Jim Bridenstine talk to astronomers when it was just beginning to be announced that we were going to go to the moon this time. And he said, I am not going to support cannibalizing the science budget to do this. He was very clear about that. He said it's been done before and did not work at all. So I think he's right. If you try to set one organization against another, one wish against another, then everybody will be unhappy. So you have to ask Congress to put their money up if they want to go and do these things. And let's not decide to cancel something else. So that's his perspective, it's my perspective, and I hope we can support that. I think we should not say, let's not go because it's expensive. We should say, if Congress wants to do it, well, let's benefit from that and share in the results.
While we're on the subject of the moon, we can do science on the moon. Look at the cosmos from the moon.
Yeah. A lot of work has been done on what is the best way to do that. No, there's a different subject, but if there's a technology to go there, then use it.
Can you say something about this new AO system you mentioned, and where does it stand? Is work being done on that? What are the prospects for that? What is the timeline?
Okay, so only very conceptual work is being done at the moment. Marlowe's team at MIT has been thinking about it. We've been thinking about it at Goddard. We are about to write a white paper for the decadal to describe what could be done. The ground-based part of the technology is probably coming along very well already, because extreme AO for exoplanets is already being done. There's a thing called MAG-AO-X for the Magellan telescope, which is already getting, or will get this year, the necessary performance at visible wavelengths, which is spectacular. But what they don't have is a star to look at in the middle of the Hubble Deep Field. We chose that field because there was no star to look at. So we could put one there for up to a few hours every few days. And that would be, I think, a huge jump forward for what we can do. So now it's only a question of, well, how do you put a little bitty laser in the satellite and aim it at the ground at the right time and place? So that should be easy. If we say we want it, we should be able to do it. Now, easy, you shouldn't listen to me about easy. You should actually find out engineers, what do they say?
Now going back to the human survival versus scientific discovery budget, is there a possibility we have a convergence in Europa? In other words, let's dwell on Europa and the possibilities that gives us. If it served as a deep space scientific research complex, and we could unplug from a lot of these other things that were kind of going down the, I guess, strange path.
Okay, that's a long, hard question. I don't have a good answer for you. I know the main advocate for Europa in Congress is no longer in office. So the trend may be to do something different now for a while. So everything has its own advocates, and we'll see what people do. So there was a question in the back, I guess?
Yeah,
Oh,
John Culberson.
yeah, John Culberson, Texas.
The Europa project that was recommended by the Decadal remains on track. And I think it's a lesson that we should rely on the community process, not go around it, and get members of Congress to support our favorite projects.
Martina.
I'm thinking of the movie Hidden Figures and the huge importance of computational efforts in all the developments of the past year. What are the main challenges that we have to face in terms of computational effort today in order to reach the goals that you are described in your talk?
Okay, well, there's an awful lot of computing and science that we're making great progress with, and you know it better than I. In the engineering world, we have vast numbers of different computer programs. And so, here's one that analyzes mechanical structures. Here's one that analyzes optical systems. Here's one that does thermal analysis. Another one that does electronics. And how do I get them to talk to each other? I'd like to just design this once and say, does this work? And do I really have to change this before we build it and launch it? And so we do not yet have that kind of integrated computing system that says, I imagine, therefore it is. So that's, I think, a tool that I would love to see, and we don't have it. So I'm hoping somebody's working on it. I would like to be able to say, okay, computer, the president agrees we're going to go to Mars. Draw me the spaceship, please. And the robot is not there for that yet.
You mentioned how many things we're launching into space now and how that could potentially start being an issue. I was wondering to what extent it's a priority of NASA's or Goddard's to try to redirect things that wind up in space and orbiting, and what's being done with that respect.
Well, I'm not sure what your concern is. I know we have international treaties that say what you're supposed to do with stuff in space. You have to make sure it goes away after a while and it does not become debris. So when SpaceX, for instance, says we're going to launch a whole fleet of little satellites, they're supposed to pay attention to that. There are regulations and they're supposed to get approval for these things. So I think we astronomers have to say, well, do we care if they do that? And sometimes we do. So the AAS has spoken, trying to protect us from troubles of that sort. But in general, as the prices of launches come down, we see all kinds of things that you might think are frivolous going up into space. The last Falcon Heavy just went up, carried people's ashes into space. Well, is that a big deal? Well, somebody thought it was worth doing. So it might not have been your choice, but it's somebody's choice. That's an interesting perspective. You know, we've got a world of many players, and no particular one is in charge. So people will do mostly what they want.
As I understand it, the regulations do not prevent someone from putting up 5,000 communication satellites that will pollute the sky, changing the appearance of starlight light sources.
Yeah,
It's an actual serious problem.
It could be. So I'm not up to date about all that, but we have to make sure we understand what that would do for astronomers. Other people, the public might say, oh, cool, I see another one. We might say, oh, that's terrible, I saw another one.
All right, let's break for the coffee break again, and let's thank all the speakers of the session.